Okay, we're going to do a very quick recap of, I think, mostly what we talked about last time, which is starting to talk about nomenclature. We covered ionic compounds. Ionic compounds are things that have a metal and a nonmetal. Or, more generally, they're things that are made up of ions, which we can typically tell because there's a metal mixed in with nonmetals. To write a formula for an ionic compound, we want to first write the symbol for both ions, that's the 1 or 2 letter code, and include the charges. The charges get incorporated as superscripts, and they follow the symbol. So for example, barium normally has a 2+ charge, so that goes in the top right. The fast way to balance these out is to crisscross them. So you take the charge, just the number part of your metal, and you make that the subscript of your nonmetal. You take the number on the nonmetal, and you make that the subscript for your metal, and boom, bam, bop, you've got your formula. And you can do that for pretty much anything. In some cases, you will also need to reduce the subscripts. So if you end up with 2's for both of them, if you end up with a 2 and a 4, you would need to reduce those to 1 and 1 or 1 and 2, respectively. We also have polyatomic ions, which I don't remember if I mentioned last class. Some of these, many of these, a decent number of these show up on the ions that you have to have memorized sheet, which is in the nomenclature lab section. These are groups of atoms. So a couple of atoms got together, usually at least 2, because otherwise it's not a group, it would just be one thing. All right, so 2 or more atoms got together, they all linked up, and overall they've got a charge. They're sharing the tab for their Dippin' Dots. That was the first thing that came to mind. Some of these are things that you have to just memorize, rote memorization. Ammonium ion, NH4+. It's like ammonia, but it's yum at the end. The acetate ion, chromate and dichromate, cyanide, hydroxide, permanganate. I think hydrogen ion, hydride, hydrogen ion, but it's negative. Mysterious. Those are also things that you just have to memorize. A bunch of these other ones, if you have a green sheet, which I don't, because that's the thing that I forgot this morning, a lot of those show up on the green sheet. You won't be able to use the green sheet on the ions quiz because we're testing your memorization, but you can use it as a helpful reference sheet. And the top section contains our oxyanions. So when we're getting to nomenclature, that's naming compounds, identifying the type of compound is very important. There are 3 classes of compounds that we need to be able to identify. The first one was ionic compounds. We talked about those on the previous slide. The second one is molecular compounds. Those are nonmetals only. And the third one is acids, and acids always have an H in front, and we'll talk about those when we get to them. We also have some common names. H2O is water, NH3 is ammonia. Ammonia is also this, what you smell if you've ever been around smelling salts, or maybe if you just are stinky. But like sweaty, stinky, and bacteria sometimes make ammonia. It's not something to be concerned about, probably. Okay, so if we've got an ionic compound, we're going to have cations and anions. We've got metals that form only one type of cation. This is, generally speaking, the ones that are shown here. So anything in our 1A, 2A, 3A groups, as well as zinc and silver, those are all going to always, every single time, 100% of the time, have the same charge, except for hydrogen, because it can also be hydride. But the rest of them, that's the case. There's also metals that can have multiple charges, and that's going to be most of the ones that are in the middle section of the periodic table, the transition metals on the periodic table. When we get out the laser pointer to point at that. Laser pointer. Right, this whole middle section, that's our transition metals. Most of them, except for zinc, silver, and cadmium sometimes also, and scandium, but we only need to worry about zinc and silver. All of those can have different charges. There's 2 ways that we can tell what their charge is, like we can tell other people what the charge is. One of them is stock nomenclature or stock notation. Thank you, Alfred Stock. This is where I would normally do the bit, we all say thank you, Alfred Stock, and then nobody does it. The other way to do it, the stock notation is where we put the charge in parentheses. That is the easier version. If you know what the charge is, you just write the Roman numeral version in parentheses. And I've got our Roman numerals for 1 through 10 up there. So for example, iron 2 plus ion is the iron 2 ion. We also have some of these common names. So the modern name, iron 2 ion. The older name is ferrous ion. Iron 3 ion, the older name is ferric ion. The common thread among all of these common names is that the OUS ending means it's the lower charge. The IC ending is the higher charge. It's not always 2 and 3. The other options are 1 and 2 and 2 and 4. I think those are the only 3 combinations that you have. And you don't have to memorize all of these common names. It's just the ones that show up on that ions to have memorized sheet in the nomenclature. My Chem 1 students have more of these to memorize. The reason that we memorize them is that some of these common names show up, especially if you go into healthcare. I'm guessing that they probably also show up a little bit in agriculture, but not as sure about that. So being able to recognize these and match them to the iron that you're looking for is helpful, it's important. So that's our cations, our metals. Our monoatomic anions, these are the simple anions. So most of our, this is like all of our nonmetals, right? They'll form, if it's just that one thing, that's the mono part of monoatomic. If it's just the one thing, we can just change the ending of that name to "ide." We've got basically all of them broken down here. So for example, fluorine is just F by itself. This would be monoatomic fluorine. F minus, it's got a charge, so we change the ending to "ide" instead of "ene," and we add ion at the end. The ion part here is a little less important for the metals. You have to have the ion part, because if I just tell you I have calcium, we'll assume that it's not charged, versus if I say calcium ion, we know that it's charged. Anytime it's F minus, we would call it fluoride, and that shows up in drinking water, and most toothpastes, I think, also have that. So when we're naming ionic compounds, the cation is going to be our first element. That's going to be our metal. We're going to name that first, just whatever the name is. It might be iron 2, it might be calcium, it might be magnesium. Just whatever the name is, we take the ion part off because we're putting it into something else. And then the anion comes after that. So generally speaking, anytime we've got a metal, it's going to be cation name followed by anion name, usually ending in "ide." There's some other possible endings as well. And we did some examples. I also pointed out that chemical names don't get capitalized. They're not proper names, so you don't need to capitalize any of them. You can just use small letters instead. If we have a metal that's one of these transition metals that's not zinc or silver, because zinc is 2+, silver is 1+. If it's not zinc or silver, we will not immediately know what the charge is. Once you get really good at it, you'll basically immediately know what the charge is. But until then, we don't know what the charge is. We have to do some math to figure it out. So what we're going to do is figure out the charge of the anion first. That's going to tell us what the total negative charge is. The sum of all the charges must be 0, so the total negative charge will be the opposite of the total positive charge. So in this example, Fe2O3, we know that oxygen is a 2- because of where it shows up on the periodic table. It's in group 6A, 6 minus 8 gives us 2-. Or we would be moving over 2 spots to get over to the noble gas column. That's adding 2 electrons. Electrons are negative, so that's a 2-. So we get the O2-. We've got 3 of them times 2-, total of 6- charge. Our iron, the 2 of them together have to balance out this 6-, which would be a 6+. That 6+ charge is going to be distributed across the 2 of them that we have. So 2 times the charge on our iron is going to give us a 6+ charge. We do a little bit of algebra. We figure out that the charge is equal to 3+. So then we could write down this is iron 3 oxide or ferric oxide. I believe iron's one of the ones that you have to have memorized. So you have to be able to produce both of those names. Do we have questions so far? Again, I go over this more slowly in that other video, which is like 40 minutes long. So I'll do the like normal speed going through the examples on that. We're also going to be working on nomenclature today. That's what we've got in lab. So if you're confused now, don't worry. You can also ask questions there. You can also go to Logan's SI sessions 1 to 3 a day, also Tuesdays. Or you could go to see some of our STEM ambassadors, our STEMbassadors, if you will, in the STEAM room over in the library, Tuesday, Wednesday, Thursday, noon to 5. They would also love to help you out with your nomenclature because it'll help them keep their job. They also like teaching. Jonathan wants to be a teacher. Tuesday, Wednesday, Thursday, 12 to 5. In the STEM room, same place Logan has his sessions. I think I sent out an announcement about it at some point. We also have polyatomic ions. A lot of these are oxyanions. Oxyanions, as the oxy part implies, have oxygen in them. If you have to memorize these, show up on your ions that you have to memorize, the ones that end in ATE are the ones that you would memorize, and these show up on the top of the green sheet. So if you turn, you have your green sheet, the one that's got 4 different sections on it, not the one that has solubility table on it, that top section, that's going to be all your ATE endings. The way that they're laid out is the same way that they're laid out on the periodic table. So borate, carbonate, nitrate, silicate, phosphate, sulfate, chlorate, in that order, left to right, and moving down rows. So those are all the ones that end in ATE. Those are the ones that you would memorize if you want to memorize the fewest things possible. There's also a version where you have 1 fewer oxygen. So a lot of those, they either have 3 oxygens or 4 oxygens. If you pull one of those oxygens off, so if it normally has 4, like in sulfate, if you take 1 off, now we've got 3, and we change the ending to ITE. It's the light version. The ITE is the light version. So we took one of our oxygens off, we removed it. The charge doesn't change, which is awesome for us. No extra charges to memorize. They either have charges of 1, 2, or 3 minus. So the 8 ending, that's the one we'd memorize. Either it has 3 or 4 oxygens, depending on the element. The ITE version is going to have 1 fewer oxygen, and the charge is not going to change. We can also expand the series. So we've got the 8s. These are the top of the green sheet. The section just below that explains these rules that we're seeing here. So it omits the ATE ending, but it tells us if you add 1 oxygen, that's also an option. If you add 1 oxygen, the charge still doesn't change, but the number of oxygens, of course, changes, and we're going to add per at the front. Per like hyper. Hyperactive, too much energy, right? Per whatever our 8 ending thing is, arguably too much oxygen. From the 8 ending, of course, we can also reduce the number of oxygens. In the case of chlorate, we go to chlorite, ClO2 with a minus. You can also take 1 more off and go to ClO minus. So we've just got 1 oxygen now. When you take 1 off from the ite ending, you add the hypo prefix. So hypo and ite go together, per and ate go together. So these are the 4 options. Not all of them have these 4 options, but that's the way that the naming works. So per, ate, ite, hypoite. And that's what's explained in that second box on the green sheet. You don't need to know all of these for all of the elements. It's just the ones that show up on that ions you have to memorize. So some of those, it's the 8 ending and the ite ending. The per and hypo might also show up on there. But if you remember the rule, you get some of those for free. So a couple fewer things to memorize. We also have in the third box on that green sheet, and some of these show up on your things you have to memorize, if you added hydrogen to the front of some of these oxyanions, to the name we would add hydrogen to the front. So CO3 2- is carbonate. If we add an H in front, now it's hydrogen carbonate. The hydrogen ion has a plus charge. The carbonate has a 2- charge. Overall, that's a 1- charge. For things like phosphate, phosphate is PO4 with a 3- charge. You can have a hydrogen in front of that. You can also have 2 hydrogens in front of that. I'm going to show us the 2 hydrogen version. So we've got 2 H's in front. They each have a 1+ charge. So that 3- loses 2. It goes to a 1- overall. This would be dihydrogen because there's 2 of them, and then still phosphate. Another weird quirk of history is that these hydrogen carbonates, for example, or things like hydrogen carbonate, sometimes instead we see bicarbonate or bisulfite. The bi means that it takes twice as much, and that's because the charge went from a 2- to a 1-, so it takes twice as many of them to, I forget what the exact context is. If you see bi in front of a thing, like a carbonate or an ite ending thing, that means that it's got a hydrogen in front. So bi also means you got a hydrogen in front in the case of our oxyanions. And then we did some examples, and that was all that we talked about for those. Question?
If that came up on the quiz or the exam where we have to write hydrogen carbonate, or bicarbonate would be okay too?
If it came up on the quiz, you could write either. If it comes up on the exam, only one of those will be present as an option because it's multiple choice. Other questions? So that's our ionic compounds. There's a lot going on there. We did that in like 17 minutes. I spent 40 minutes on that, maybe even less material in lab last time. So again, you can go watch that. Pump up the views, smash that like and subscribe button. You know what to do. And then we're going to move on to our second category. So I prefaced by saying that there were 3 categories. My Gen Chem students get 4 categories. My Chem 1 students get 4 categories. We're just going to stop at 3. So our second category is molecular compounds. The first step in naming a molecular compound is identifying it as one. Molecular compounds are nonmetals only. They don't have ions. They don't have charges in them. So we need a different naming system to be able to name our molecular compounds. So molecular compounds, 2 or more nonmetals. We are going to learn the simplest version of molecular compounds, which is binary 2-element molecular compounds. So it's just going to have 2 things. It gets more complicated when you add more things. So we're going to keep it simple. I had a thought somewhere, but I lost it. With our molecular compounds, we use prefixes. So prefixes are given to each of the elements. This indicates the number of atoms that are present. They are all of these ones that we see here. A lot of these, I think, you probably would recognize if you saw them just like out in the wild. You'd be like, oh, I know that prefix. I've seen that before. That's most of these. So mono for 1, di for 2, tri for 3. Tetra might be a weird one for you, but that's for 4. Penta for 5, like the pentagon. Hexa for 6. Hexa has an X in it. 6 also has an X in it. Then we've got our first weird one, hepta. Hepta is for 7. Octa, like the octagon or octopus. I'm going to write octopus has 8 legs. Hopefully we knew that. And then nona not like grandmother, but I pronounced it that way for 9. So the arrows there are for the ones that are maybe a little weird to remember. And then the highest number that we're going to on this chart is deca, like decade, 10 years. So we use these based on how many of each element we have. That indicates the number of atoms that we have of each of the elements. Questions about any of those? Okay, somebody remind me to talk about hydrates, because I don't have hydrates in my slides, but we need to talk about hydrates. And that's not just drinking enough liquids, but it's related. Could have turned that into a liquid IV commercial. If there's only one atom of the first element, the prefix mono is normally omitted. That's our one weird rule. I think that's the only one weird rule. So for example, CO2, the first element is carbon. We've got one of them. So normally we would call this monocarbon. But we cross out the mono because we just have one of them and that's our rule. We don't need to include it. That's the only time that we exclude our prefix for our first element. For the oxygen, the base name is ox. We add the prefix of di because there's 2. And we also change the ending to IDE. So we would call this carbon dioxide. Sometimes our prefix will end in a vowel and our base name will start with a vowel. And the first vowel is sometimes dropped. This is not something that you would lose points for if you didn't do it. It's more of a convention thing. It's also how we pronounce it. It's realistically not that important. It's sort of for those of us that speak more than one language or attempt to, right? If you're talking in your non-native tongue and you say something that's a little bit off, like the grammar's not quite there, a native speaker usually just kind of gets what you mean. This is one of those moments. Any chemist who's not something that I'm not going to say on a recording, will understand what you mean and is not going to have a problem with it. They'll know what you're talking about. So an example of this would be for N2O. N is nitrogen. We've got 2 of them, so we put the di prefix in front. So di-nitrogen. We have 1 oxygen. Our prefix for 1 oxygen is mono. Oxygen also starts with an O, so this would be monoxide instead of monooxide. If you write monooxide, everyone still understands what you mean. Nobody's going to criticize you for it unless they're a jerk, or it's me correcting you just like, hey, just as a reminder, this is what we normally do. It's not something you'd lose points for. And that's molecular compounds. So let's name some molecular compounds. First we have N2O4. So naming N2O4, what is our first element? First element is N, which is nitrogen. How many nitrogens do we have? We have 2 nitrogens. What's our prefix for 2? A little aggressive, okay. Dinitrogen. What's our second element? Our second element is oxygen. The base for that is going to be ox. How many of those do we have? We've got 4. What's our prefix for 4? Our prefix for 4 is tetra. So it would be normal and reasonable and understandable if you wrote tetra-ox. And then how do we change the ending? We turn it into ide. So dinitrogen, tetraoxide. This is probably one of those instances where we would remove one of these. So I would probably remove the A. We'd pronounce it tetroxide. Again, any chemist would understand what you meant if you said tetraoxide. Wouldn't be a problem. Okay, go ahead and try naming the compound NH3. Do not use the common name. There is a common name for this one. All right, what is our first element? It's nitrogen again. So we've got nitrogen. How many nitrogens? One. One nitrogen. What is our prefix for one? So are we putting mono in front? Why not?
Because it's the first element.
Because it's the first element, and that's the rule. That's all the explanation that I have for you for this one. Sometimes I have more explanations. I'm going to write the mono in, and then I'm going to cross it out so that we can see that it doesn't need to be there. So no mono, thank goodness, just nitrogen. What comes after the nitrogen? What's our second thing? H. H is hydrogen. The base for hydrogen is not that, it's this. HYDR, we take off the ogen. How many of those do we have? We've got 3 of them. We put our prefix for 3, tri, like Triforce. And then what do we do to the ending?
Ends in ide.
Yeah, we change it to ide. So we would call this nitrogen trihydride. The common name is ammonia. That looks like I wrote ammonia. Ammonia. Any questions about molecular compounds? It's a little bit simpler than our ionic compounds, one could say. Then we've got acids. Acids are also molecular compounds, but they're a different category of them. So these are still molecular compounds. These form ions when you dissolve them in water. So strictly speaking, a lot of these have to be dissolved in water for them to qualify as being acids. If they're not dissolved in water, then they're not acids, they're just molecular compounds. I'm not going to make a big stink about that distinction. For our acids, hydrogen is the first element. So hydrogen shows up first, and then other stuff shows up after that. Normally, hydrogen doesn't come first. So this is our key that we're looking at an acid. This is not always the case, but in my class, I like to put the hydrogens first so that it gives you a nice, reliable cue that we're looking at an acid. And then we're going to have some nonmetals after that. We've got 2 groups for our acids. The first group is binary acids. Binary means 2 things. So these are going to contain hydrogen and a nonmetal, or there's one specific thing that I'm thinking of here, a polyatomic ion, not an oxyanion. Because our second group, I'm really fumbling with the controls here, one sec. The second group is oxyacids, the oxy here meaning oxygen. Our oxyacids have an oxyanion. So any of the ones that is up in the top 2 sections of our green sheet, any of those ones, anything that ends in ate or ite, that's what we're talking about here for our oxyacids. So a polyatomic anion that has oxygen in it. For naming binary acids, where we just have 2 things, these are composed of hydrogen, the first thing that we'll see, and a nonmetal, which is the second thing that we'll see. Our naming convention for these is they start with hydro. This is unique. This is unique to binary acids. This is our one big cue that we're looking at or talking about a binary acid as opposed to any other type of acid. So we'll have the hydro prefix. We'll take the base name of the anion. We'll add ic to it, and we'll add acid to the end. The acid part at the end is our dead giveaway that we're talking about an acid. But that was probably clear to you. So for example, HCl, the AQ here means it's aqueous, meaning it's dissolved in water. That lets us call it an acid. So HCl, we've got an H in front, that lets us know it's an acid. It's just two things. We put the hydro prefix, we take the base name for chlorine, which is chlor, we add ic to the end, and we also tack on acid as our second word. So HCl is hydrochloric acid. We do the same thing with HBr. We just swap out the chlor for brom, so it's hydrobromic acid. Hydrochloric acid is sometimes used in toilet bowl cleaners, especially the ones that say that they remove rust rings. Those usually have hydrochloric acid in them. So for naming binary acids, we can name HF. What kind of compound is HF? Is it an ionic compound, a molecular compound, or an acid? We should know this one. It's an acid, thank you. So it's an acid, and what kind of acid is it? Is it a binary acid or is it an oxyacid? It is a binary acid. We got some clues on the screen. So yeah, it's a binary acid. So it's just two things. We need to include what? What's special and unique about binary acids when we name them? Yeah, it's this hydro. So we have to start off with hydro. And what's our thing that's not hydrogen? F, fluorine. So we're going to take the base for fluorine, which is fluor, F-L-U-O-R, not flour, F-L-O-U-R. That's a common mistake. We're going to change the ending to ic, and we're going to add acid to the end. So HF is hydrofluoric acid. Hydrofluoric acid is probably most well known for showing up in Breaking Bad in the first season. It's what they used to dissolve that bathtub, which is of course not their primary intended use, but that's what happened. We also have this other binary acid, H2SE. What do we need to include for H2SE at the front? We do not need di, as I'll explain in a second, but we do need the hydro. So we need the hydro, and then what is Se? What element is that? Selenium. And so we're going to take the selen part, that's our base. We're going to change the ending to ic, and we'll write acid. The reason that we don't need the di is if we look at where selenium is on our periodic table, it's under oxygen. Oxygen takes on a 2- charge. Selenium also takes on a 2- charge when it's an ion. Se2-, to balance that out with hydrogens, which have a 1+ charge, we would need 2 of those, which we can see if we swap and drop. So that's how we get the formula of H2SE. So it's sort of similar to an ionic like flow for how we're doing this, because we can figure out the number of hydrogens based on the charge. It's always just going to match the charge. So if we had something from our 5A group, like nitrogen or phosphorus, those are going to have a 3 negative charge. So how many hydrogens would we need in the front? Also 3. Like this. So we'd have H3P, which would be hydrophosphoric acid, assuming it exists. One of the fun things about nomenclature is that we can make up names for things that aren't real, that don't exist, which is awesome because then you look them up on the internet and you're like, what? This doesn't exist. Yeah, but we can still play with the names. It's fun hypotheticals. So that's our binary acids, relatively easy. Our oxyacids involve a little bit more work. Most of that work comes in the form of remembering our names for our oxyanions. This is where the green sheet can be especially helpful as we're learning, as we're practicing our oxyanion names. You will not have the green sheet on exams, but you will have a periodic table, and you'll have everything that you've stored away in your brain. So as long as you've studied your oxyanions, the oxyacids shouldn't cause you too much trouble. So our oxyacids have oxyanions. For example, HNO3. If we take off the H in the front, we're left with NO3. The H as an ion has a 1 plus charge, so the NO3 as an ion must have a 1 negative charge. We can also just see the NO3 and match that up with, on our oxyanions table, NO3 is the one that shows up in that top table. It says that that's nitrate, so we could identify that as the nitrate ion. In the case of H2SO3 and H2SO4, we would have to maybe do a little bit of rearranging. So SO4, 2- is our sulfate. Take one oxygen off, SO3, 2-, that's our sulfite. The number of H plus in the front balances the charge of the oxyanion. So for example, phosphate, PO4 3-, because it has a 3 negative charge, we have to put 3 hydrogens in front. It's the same thing we're doing with our binary acids. We just have oxygen in there as well. Same sort of idea. When we're naming oxyacids, it's important that we know the names of our oxyanions. There are 2 possible name change options. We've got oxyanions that end in ATE. We take the base name of the oxyanion and we add ic acid. So we change the 8 for ic. So our first rule, 8 turns into ic, and we add acid to the end. Our other option is acids with oxyanions that end in ite, so the light form, 1 fewer or 2 fewer oxygens. If we have 2 fewer, we would just have the hypo prefix. So if they end in ITE, they're going to have this form, still the base name of the oxyanion. We change that ite ending to OUS, and we add acid to the end. So ite turns into us, and we add acid to the end. So if you want to remember how to name oxyacids, just repeat to yourself, 8 ic, ite us, 8 ic, ite us, 8 ic, ite us. Just ad nauseum, that's until you're nauseous. Or until you just get tired of it and you want to stop. So 8 turns to ic, ite turns to us. 8, like something that you consumed. Ic, like gross, that's nasty, would normally have a K, but that is maybe how you can word associate those 2 endings. 8 and ic go together. I don't know how to name associate ite and us. So those are our 2 name change options for our oxyacids. Again, the hard part, I think, is figuring out which oxyanion we're working with. Once you get good at that, the naming for these really becomes pretty simple. So naming some oxyacids, we have HNO3. Looking at HNO3, we can tell that it's an acid. It's got an H in front. H in front, it's an acid. So that tells our brain, all right, we're going to work through our acid naming pathway. We have to identify, is it binary or is it an oxyacid? We've got oxygen in there. So it's not a binary acid, it's an oxyacid. So NO3 is the other thing. For now, what we would probably do is find NO3 on the oxyanion table, or in our ions that we have to have memorized. It might show up there as well, probably does. So we go to our oxyanion table, we would find the one that looks like NO3, NO3 minus. So NO3 with a 1 negative charge is nitrate. What ending does nitrate have? 8. It's got the 8 ending, so we turn it into what? Ic. So nitric acid. That's it. We're having a good time. Our other one, I'll give us some time to work on. Okay, reining us back in. We've got H2SO3. We see the H is in front, and we know it's an acid. That's our cue that we're working with an acid. We've got H in front. It doesn't normally go in front unless we're working with acids. The rest of the thing that we have is this SO3. SO3 looks like our 8 ending form for sulfur, SO4, 2 minus, which is sulfate. They're similar, but they're different. Can you spot the difference? That was way more, that tone came across, I think, probably way more condescending than I intended it. HR wants you to find the difference between these two images. I think is maybe a better way of saying that. What's different? What changed? Number of oxygens changed, right? We've got 3 instead of 4. 3 is smaller than 4, 1 less. When we take 1 off from our ATE ending, it changes to ite. 1 fewer oxygen ending is ite. So what we have, SO3, it would also have a 2 minus, is sulfite. And that ite ending, when we make it an acid, turns into what? Us. We are sulfite. So it's sulf, and this is going to mess with some people. You're us, acid. So it's sulfurous acid. If you wrote sulfus acid, guess what? Chemists will still know what you're talking about. It's just not normally what we do. So sulfus acid, that's close enough. But you should ideally write sulfurous acid, because that's how we write it. One of the fun things about having chemistry be so old, we do weird things like that sometimes. All right, I'm going to give you 2 more to work on for oxyacids. So find, what does that oxyacid look like? Which one does it look like? How did we change it? How does that change our name? Okay, we're coming back. Lots of people got these right. At the very least, lots of people identified that we were working with oxyacids. We may not have correctly identified all of the nuances and intricacies and subtleties of all that sort of stuff. That's okay. We're still learning. So for HNO2, the H in front tells us it's an acid. The NO2 part, we're looking for something that looks like NO2 if we're using our green sheet. And that thing is NO3, which is nitrate. We do not have NO3 because we have NO2. That's one fewer oxygen. NO2 is nitrite because we took one of the oxygens off. And it has to have the minus, otherwise it would just be a molecular compound. So NO2 minus is nitrite. We change the ending of ite to us, and we add acid to the end. This is nitrous acid. And then for HClO4, we have this ClO4. ClO4 looks like ClO3 minus, which is chlorate. We added one oxygen. What does that do for us? What do we add? What do we change? Per. So this is perchlorate. That's the anion that we have. So we have to add the per prefix to indicate we added one oxygen. So this is going to be per, keep the base chlor, and what do we change the ending to? Ic. So it's perchloric acid. Questions? All right, so we've been looking at all of these examples, kind of one section at a time. That's not how things are in the world or in the nomenclature worksheet. Some of the sections of the nomenclature worksheet, it's all of them combined together. We're going to first go through them part by part, so we'll get some practice, we'll get some repetitions in for each of the individual sections, and then we're going to combine them all together. This is sort of like if you're working on the choreo for your favorite TikTok dance, if you have one, right? You would work on some of the individual parts first, and then you would, at the end, right, you'd put them together. I don't dance, so that's why it looked so weird when I was moving my body in that way. So we're going to do a similar thing. This is the flow chart from our book, MacArthur Chemistry 3A version 1.2 on Libre texts. It's free. You can look at it on the internet. So we've got ionic compounds. The smallest unit is formula units. Our clue for these. So you've got a metal and a non-metal, or you've got something with polyatomic ions. The way that we name these is in the next box. We're going to name our cation first. We name the ion last, the anion last. We're not going to use prefixes. No prefixes for ionic compounds. We've got mixed in with some options. It's a little different than the way that I structure it in my slides. But we've got things with a metal and a non-metal. These are going to have the IDE ending. Things like NaCl. Na is always the same charge. It's sodium. It's always a 1+ charge. So we just call it the sodium ion. When we mix that together with our Cl-, our chloride ion, let's zoom in. Our chloride ion, that becomes sodium chloride. We can also have stuff with variable charges. That's basically just our transition elements except for zinc and silver. All the other ones like manganese, iron, cobalt, nickel, copper, chromium, vanadium, etc. Those can all have different charge values, and so we would have to sleuth out, figure out what the charge is first, and then we would include it in parentheses and Roman numerals if we're using stock notation. Thank you, Alfred Stock. Or in the case of things like iron, we would call it ferrous ion, because iron is one of the 2-3 options for its charge values. With polyatomic ions, we just name the polyatomic ion as is, and the other rules apply from our metal, non-metal thing that we were talking about before. We've talked about all of this earlier today. This might be helpful for you. There's other flowchart and diagrams out there on the internet that can also help you navigate nomenclature. And then we've got a little combined nomenclature exercise. Let's work through them together because I still want to have time to talk about hydrates. So first thing first, what kind of compound are we dealing with PCl3? Is it ionic, molecular, acid? It is molecular. It's molecular because what kind of elements do we have? It is nonmetals only, which makes it molecular. Molecular compounds use prefixes. What is our first element? Phosphorus. How many phosphoruses do we have? 1. Our prefix for 1 is mono. What's our other element? Chlorine. The base for that is chlor. How many do we have? We've got 3 of them. So we're going to add what? Tri. And how do we change the ending? We change it to "ide." What is wrong with this? Mono. We have mono, and we do not want to have mono on our first element. So monophosphorus, no. Phosphorus, yes, stonks. Phosphorus trichloride. I like to include some of those where I do something wrong, just to help us recognize sometimes we'll do stuff wrong too. And then we can talk about what we did wrong. What kind of chemical is HClO? It's an oxyacid. How do we know that it's an acid? It has hydrogen in front. We know that it's an oxyacid because we've got an oxyanion. The oxyanion that we have is ClO. ClO looks like heaven. Sounds like heaven. But it looks like ClO3 with a 1- charge, which is chlorate. What's different? 2 fewer oxygens. If we take off 1 oxygen from the 8 ending version, how do we change it? We change it to ite. So ClO2- would be chlorite. If we wanted to do another one, how would we change it? Yeah, we had the hypo, so ClO-, hypochlorite. Since it's an acid, how do we change the ending? We change it to OUS, so this would be hypochlorous acid. Next one up, we've got CaOH2. What kind of compound do we have with CaOH2? Ionic, molecular, acid. It's ionic. How do we know it's ionic? It's got a metal in there. So Ca is a metal. It's calcium. It shows up in our group 2. It's an alkaline earth metal. So this is ionic. Already gave away the game a little bit because I said that it was in group 2. Why is that important? It's also the charge. We know what the charge is. That's important. It's always going to be calcium 2+, which means for us, we don't have to specify what the charge is. We just write calcium. And then what is OH? OH is hydroxide. That's one of our polyatomic ions that you have to memorize. So this is calcium hydroxide. That's all that we have to do for that name. No prefixes, because the charges will work themselves out. We'd be able to work back to it. We don't have to include the charge of the calcium because it's always calcium 2+. We don't do any name change things because it's a polyatomic ion, so it just stays as hydroxide. And then for D, we've got Ni3PO42. What kind of thing is that? This is also ionic. How do we know it's ionic? We've got a metal. Ni is nickel. Where do we find nickel on the periodic table? Yeah, it's one of our transition metals, so we don't know what the charge is. So we have to do some sleuth work. So nickel is a transition metal. We've got nickel, who knows what, plus. We'll figure it out. The way we'll figure it out is by looking at our PO4. What's PO4? It's phosphate. And it has a 3- charge. So we get to do a little bit of algebra. We've got the 3- charge. How many of those groups do we have? How many phosphates do we have? We've got 2 of them. 2 of them, each of them has a 3- charge. If we multiply those out, 6 negative charge. What will balance out 6- and make it 0? 6+. So our nickels altogether have to add up to a 6+ charge. We've got 3 of them. So 3 times whatever the charge is on our nickel is going to give us a total of a 6+ charge. The number that does that for us is 2. So this is nickel 2 phosphate. So if we've got transition metals and we have oxyanions, it does become a little bit more involved. There's more steps, more hoops to jump through, but we can still manage it. We just have to work step by step and maybe also have a system for figuring out our charge. If you're great at algebra, you can do that mental math in a pinch. Awesome. It's easy, it's fast. Otherwise, for the rest of us, we'll have to work on some systems to figure out that naming. And then last but not least, we've got HF. And HF is what type of thing? It's an acid. It's a binary acid. Our binary acids have the prefix hydro. We take the base name FLUOR. We change the ending to ic, and we add acid to the end. A couple of things that I'd like to show us. If we have HClO3 and we have HCl. HClO3 is an oxyacid. ClO3- is chlorate. So HClO3 is chlor. Change the ending to ic and add acid to the end. HCl also has chlorine as its base. We know that it's supposed to have a hydro in front. Let's pretend like we don't and see what happens. So we'll take the base, chlor, change the ending to ic, and add acid. Those are the same name, and that's a huge no-no in chemistry naming. This is a problem because chloric acid needs to refer to only one of these. This is the reason that we have the hydro prefix for our binary acids. That's all that I wanted to show us here. There's a reason that we have the hydro there, and it's so that we don't get, that's the wrong tool, we don't get these two things, HClO3 and HCl, mixed up. The other thing that I wanted to talk about is hydrates. Hydrates are ionic compounds if you are well hydrated, what does that mean that you've been doing a lot of? Drinking water. You're full of water. These are ionic compounds with water. I think that one of them, I think that a real hydrate, I think calcium sulfate, let's just say that it's 2H2O. Okay, so something, a feature that we've got here. This middle dot means associated with. This is not the multiplication sign. We're also not doing the unspeakable horrors of linear algebra here either, because that middle dot means a thing in linear algebra. Flashbacks. Okay, so this middle dot means associated with. For every one of these calcium sulfate units, every one of these things, we're going to have two waters that are also in there. So ionic compounds, salts, like to pick up water. They'll often absorb it just straight out of the air. They'll do that to the point that they can't fit any more waters. And for this one, we're pretending that it's calcium sulfate with two H2Os on it. This two H2Os part, the H2O, we call hydrate. So our name for the CaSO4 part would be calcium sulfate. We've got some waters, so we have the hydrate part. Does anyone want to guess what we're going to use to signify that we've got two of them? It's di. So this is dihydrate. It's the same prefixes that we used for molecular compounds. But for water molecules. Questions about that? We will see it show up places. Hydrates also usually have a different look to them. Oftentimes they have fun colors. And that's all for chapter 3.